Qubits and Chill, relax. It's just linear algebra with drama.
Welcome to Season 1 of this course. This is the first real lecture. In this episode, we are not going to prove anything. We are not starting with heavy mathematics. Instead, we will do something very concrete. We will build a simple quantum experiment, run it many times, and learn how to read results. If you can understand this experiment, you already understand the core idea of quantum computing at a practical level. Before we start, let me be very clear about the assumptions. I assume only three things. First, you know how to use a computer. Second, you have a basic intuition about randomness like a flipping coin. Third, you have the Python and Qiskit installed from season 0. That's it. You do not need linear algebra, you do not need quantum mechanics, you do not need to know Nielsen and Chang. Those things are coming later, but not today. By the end of this episode, you should be able to do 5 things. Explain the conceptual difference between a bit and qubit. Understand why one measurement is not enough. Explain why repetition reveals probabilities. Read a measurement histogram. And finally, run your first quantum circuit. If you can do this episode is a success. Let's start with something familiar. The classical bit. A classical bit stores a definite value. At any moment, it's either 0 or 1. If a bit stores the value 1 and you read it, you get 1. If you read it again, you still get 1. Reading a classical bit does not change anything. This is why classical systems are deterministic. Same input, same internal state, same out. Repeating a measurement in classical computing gives you no new information. It only confirms what you already know. Now, this is where things change. A qubit is not a fixed value before measurement. A qubit is described by a state and it produces probabilistic outcomes. This does not mean that the qubit is half 0 and half 1. That is a very common misunderstanding. What it means is this. The state defines the probabilities of measurement outcomes. When we measure a qubit, we still a classical result. 0 or 1. Nothing strange appears. The difference is not in the result. The difference is in how that result is produced. Here is the key idea. If you measure a qubit once, the result looks random. And from a single measurement, you cannot describe the quantum state. If you get 0 once, that does not mean the qubit was 0. To understand the quantum state, we must repeat the same experiment many times. What matters is not one result, but the pattern that appears. Before we draw circuits, we need to clarify one notation. You will often see symbol like this, and this is called cat 0. This symbol does not mean absolute value. Cat 0 is the name of a state, not the number 0. Measurements produces numbers. States are something different. For now, this intuition is enough. We will do the full mathematics in later seasons. Now, we are ready to build our first quantum experiment. We start with one qubit. And by default, the qubit starts in the cat 0 state. If we measure cat 0 immediately, result is 0. We always get 0. So we need to change the state before measurement. How do we transform a state? In quantum computing, we do this using gate. The simplest gate for this purpose is the Hadamard gate. For now, we only care about its effect, not the mathematical details. Our circuit looks like this. We start in cat 0, apply Hadamard gate, and then measure. You can see the representation here. And what measurement gives us is measurement returns a classical value, either 0 or 1. A single run gives us one result. That result alone tells us nothing about the state. So we repeat the same experiment many times. Each repetition is called a shot. 1000 shots means 1000 measurements. For this circuit, we expect roughly 50% zeros and 50% ones. Not exactly equal every time, but close. We visualize this using a histogram. The histogram shows how often each outcome appears. This is how we read probabilities in practice. At this point, let me be very clear. This level of understanding is enough for practice. You can already build circuits, run simulations, and interpret results. We are intentionally not doing the full theory yet. In later seasons, we will describe these states mathematically, prove where these probabilities come from and connect everything to quantum mechanics. For now, this intuition is exactly what you need. Now, let's test our prediction.
So far, everything we did was theory. We built intuition and made a prediction. Now we are going to test that prediction using code. We will build exactly the same circuit we discussed on paper. First, we import the basic tools we need from Qiskit. Quantum circuit lets us build circuits. AER gives us a simulator, and plot histogram is used to visualize the result. Second step is create one qubit circuit. Now we create a quantum circuit. This circuit has one qubit and one classical bit. The qubit stores the quantum state, the classical bit stores the measurement result. By default, the qubit starts in the cat's zero state. The third step is apply the Hadamard gate. This is the gate that creates a balanced quantum state. Remember, we are not focusing on the math there. We only care about the effect. The fourth step is measuring the qubit. Measurement converts the quantum state into a classical result 0 or 1. After this step, the quantum part of the experiment is finished. Next step is choosing simulator and run. We run circuit using 1000 shots, meaning 1000 repeated measurement. After this step, we visualize results. Counts show how many times we measured 0 and how many times we measured 1. Now, we plot the histogram. As expected, we see roughly 50% zeros and 50% ones. The exact numbers are not perfectly equal because we use the finite number of shots. If we increase the number of shots, the histogram becomes smoother and closer to expected distribution.
At the end of the course, I give you a mini task. Build the same 1 qubit circuit, apply a Hadamard gate, measure, then run with 1000 shots, save the histogram as a screenshot. Then you have just run your first quantum experiment.